Hey everyone, welcome to a video about resonance and delocalization of electrons, where we'll talk about what those two things are and practice drawing resonance forms. So, what is resonance and what is delocalization? These terms can be used interchangeably, so sometimes it can get a little bit confusing, but both of them are hitting at the same sort of core point. So, I'm going to give you my definitions for these two terms, but you'll see how they're very similar in just a moment. Resonance, or what you'll probably hear more commonly referred to as resonance forms, refer to an alternate arrangement of electron density. What that means is that in a resonance form, we can change the position of some electrons, but it doesn't constitute any kind of chemical reaction, and it is only going to change the location of the electron density, but not the actual overall sigma bonding structure of the molecule. Delocalization is kind of what the name sounds like. We could have electrons that are localized in one position, but electrons that are delocalized means that they can exist over several positions or several atoms, and they are linked by resonance forms. Sometimes when we talk about the delocalization of electrons, we mean that they're extended over a very long distance consisting of many, many atoms, but we could also talk about the delocalization of electrons between even just two atoms. Let's take, for example, a simple resonance form of acetone. The carbonyl functional group that we see in acetone is kind of the poster child for resonance. We love to think about the resonance forms of carbonyls because they explain the reactivity that we see for carbonyl-containing compounds. We can take those carbon-oxygen pi bonding electrons and move them around using our curved arrow formalism. So you might see an arrow that looks like this, depicting these two red electrons going up to sit on the oxygen alongside its existing lone pairs. And that would give us a resonance form that looks something like this, where we haven't changed the sigma bonding framework at all. We didn't touch these lone pair electrons, so they're still there. But the double bond that created that carbonyl has now been broken, and those two electrons reside on our oxygen. The uneven distribution of electrons here gives this oxygen a negative charge and the carbonyl carbon a positive charge. As I mentioned before, this resonance or movement of electrons is not the same as a chemical reaction. So you should notice that we're using a slightly different type of arrow here than we normally do. This is a resonance arrow. This double-headed resonance arrow is specifically for showing the change between two resonance forms and is not the same as a chemical equilibrium arrow. For more information about arrows, make sure you check out my arrow drawing etiquette video. As we go about looking for and drawing resonance forms, we want to be aware of some of the chemical motifs that will allow resonance to occur. One of the key takeaways here is that you need alternating single and double bonds in order to achieve resonance. And there's a couple of different ways that this can occur. The first one is when you only have pi bonds, you don't have any other heteroatoms with lone pairs or charges. We can resonate through these double bonds because their p orbitals are aligned such that there's nice overlap that allows the movement of the electrons to occur. When looking for this alternating single and double bond motif in a molecule, just start anywhere and kind of count along as you go to see if they are truly alternating. Sometimes they can look like they're close enough to be able to resonate, but it helps to just count it through step by step to be sure. So if we start at this end here, we could say there's a double bond, followed by a single bond, followed by a double bond, followed by a single bond, etc. You get the point. So these could all resonate with one another, and we could draw arrows for that, which look like this, moving the pi bond along to a single bond, and then that pushes the next pi bond over. This last one doesn't have any further to go, so we're going to have to push the electrons onto that carbon. So I'm not going to draw this resonance form here. This is just to remind ourselves that we need this double, single, double type of motif when we're looking at neutrally charged molecules that don't have any lone pairs available. When we do have lone pair electrons or a negative charge would behave the same. We want to make sure we have a similar motif in place. We still need that pi bond. So if we look for that in this example below, we have our pi bond here, and then there is a single bond here, followed up by a lone pair of electrons. Either lone pair would work here, but it's important that we have this single bond between the two. Otherwise, we wouldn't have the alignment of orbitals that we need in order to push the electrons through them. So let's practice drawing our arrows here as well. We want to start with one or the other pair of electrons, move those down onto the sigma bond, and push the pi bond over to the end. Again, we'll practice actually drawing out the resonance forms for these arrows in a moment. So while this motif is a little bit different, hopefully you can see the similarities that we want to have a double bond and then a single bond, And then instead of another double bond, we use that pair of electrons. Lastly, if we have a positive charge, it doesn't seem like there's a lot of electrons there to push, but there is an empty p orbital instead, which we can use electrons to fill in kind of the opposite direction. So yet again, we want to have that alternating motif present where we have a double bond, single bond, and then at the end of that single bond needs to be the positive charge. So we could draw an arrow for this, which is going to take these pi bonding electrons and move them over to help fill in that positive charge. So even though these motifs are not exactly the same, we can find the similarities to help us be able to see the patterns more quickly. Before we do a couple examples, just a few more thoughts about what resonance is and isn't. So we like to talk about resonance forms. In OChem, you're going to draw a lot of resonance forms, and I hate to tell you this, but none of them are real. But even if they're not real, they're super, super helpful tools for us to be able to understand why molecules react the way they do. Think of it like this. Let's say a friend of yours is running in a track meet and they asked you to document the race for them. When you got there, you could take some pictures with your camera, but when you look at each picture individually, you don't really understand how the race was run or what distance it was. So each picture is like a resonance form. It gives you some information like the runner was here or they were there, but it doesn't really tell you that much about the actual race itself. Each resonance form does have some validity to it, but it's not really representative of the whole picture of the electronic structure of the molecule. We do say that the resonance forms contribute to something that is really true and real, and that is the resonance hybrid. The resonance hybrid is like a weighted average of all the resonance forms that contribute to it. It's more like telling someone about your friend who ran in the track meet. You could say they ran the 100-meter sprint. The person you're telling this to won't be able to see your friend at any position along that 100 meters, but they'll know the important outcome of the race is that your friend will have covered that 100 meters even if they couldn't see your friend at each position along the way. We'll practice drawing resonance hybrids in another video for the examples that we're about to do next. Just keep in mind that resonance forms are useful, but they're not really telling us the whole truth, and for that, we need to refer to the resonance hybrid. In order to get to this resonance hybrid, though, we have to know what the resonance forms look like, so let's practice drawing a few. Let's start first with this example of a charged molecule. Now, there are a lot of different ways to draw resonance forms, so you can start wherever you like. I personally like to start at lone pairs of electrons, if there are any. And I'm seeing a couple lone pairs on this oxygen here, which are adjacent to this positive charge. So this is a little bit of a different motif than we've seen so far, but we have here electrons, single bond, place where electrons can go. That will still fit our motif. So we can use a red arrow to draw these electrons falling down onto that single bond to form a double bond. And now I'm going to use a red resonance arrow to draw what that resonance form would look like. My favorite way to draw resonance forms is to first draw in all the sigma bonds because none of those should have changed. Then I'll draw in any other pi bonds or things that didn't move. So those two pi bonds didn't move, and we didn't use that lone pair of electrons. But we did make a new pi bond here between that carbon and oxygen. Then make sure you check for formal charges. We want to make sure our charge balance is always the same. We started off with a positively charged molecule. We must end with a positively charged molecule. And now that this oxygen has three bonds and only one pair, that's the part that's going to have the positive charge on it. But there are multiple different ways that we could go about moving these electrons. Using those lone pair of electrons is one way. Let's see if there's a different way. If we're looking for those motifs, here we have our positive charge, single bond, and a double bond right there. So we could use that pi bond to resonate as well. I'm going to draw this with blue arrows. If we take those two pi bonding electrons and let them fall down onto that sigma bond and fill in that positive charge, we'll get something that looks like this. Again, draw your sigma framework in first. This time, the lone pairs on the oxygen and that final pi bond don't change, but the one in the middle has. It's moved to that position. Number your carbons if you need to. And since we removed electron density from this carbon here and didn't form any new bonds, that now has the positive charge. Sometimes drawing these resonance forms will almost lead you down a path. For that reason, I like to only draw one or two arrow pushing arrows at a time so that I don't miss any of the resonance forms. You can draw a whole lot of arrows all at once, but for the most part, that gets confusing to read, and you can often miss resonance forms when you do too many arrows at once. So I recommend just doing a couple of arrows and then moving along in a path. We'll see that here. Now that this positive charge is in a slightly different spot, it can resonate using this motif here of double, single, and positive charge. We'll draw that in purple, showing this double bond kind of scooting over to fill in that positive charge there, and that will give us a resonance form that looks like this. Again, start with your sigma framework. This pi bond near the OH didn't change, but now we moved the other pi bond in, and the positive charge has now ended up on that methyl group. While drawing resonance forms and pretty much any arrow pushing that you do, make sure that you're only ever moving electrons. It may be tempting to pick that positive charge up and put it somewhere, but your positive charges are never going to move. They're only going to get rearranged because of the movement of electrons. So here we have three resonance forms of the initial molecule that we started with. And again, none of them is necessarily the entire story here. They all represent snapshots that you could see if you took a picture of our resonance hybrid. Now let's move on to this neutral example. Again, you can start wherever you like, but I like to start with the lone pair electrons on this nitrogen. Let's take a look and see what motifs we have available to us and where we can resonate. So if we start with the electrons here, we could go up to the top where we have a single double bond adjacent to our electrons. That could work. We could similarly start at the electrons in blue and go single double down the side, or I think you see where I'm going with this. In purple, we could go single double down the opposite side. So here, kind of similar to our example above, we have three different possibilities for resonance forms. Let's start with the first form in red. We'll take the lone pair electrons, lay them down on that sigma bond, and then move the pi bond over like so. That will give us this form. Again, draw all of your sigma bonds first. Those haven't changed. Draw in the pi bonds that didn't change. But now we made a new pi bond from carbon to nitrogen there at the top and moved a pair of electrons out onto that methyl group to give a negative charge. Now, check yourself before you walk away. We made a negative charge, but we didn't have one to start, which means that we also need a positive charge. And since that nitrogen now has 4 bonds and no lone pair, it is the part that must be positively charged. If we have a negative and a positive together, we're neutral overall and we're in the right spot. So we could take the same pair of electrons in an alternate resonance form, move those down along the sigma bond, and push the pi bond over. That will give us a form that looks like this. Now, nothing has changed at the top of our molecule or on the right-hand side, but on the left-hand side, we made a new carbon-nitrogen double bond and put the lone pair of electrons there at that corner for our negative charge, and not forgetting our nitrogen with the positive charge. Last but not least, in the purple form, we could do the same on the opposite side of our molecule. And we'll draw a really long resonance arrow so that we can get out to this form out here. In this example, all three resonance forms kind of came directly from the original molecule that we were given, but that was not the case in the previous example. In the previous example, we had to take one of the resonance forms and then work with it further. So when drawing resonance forms, you should consider if a resonance form has the potential to resonate further, or if you should go back to the original and look for a different motif that would allow you to resonate in a different direction. Hopefully, these examples have given you a little bit of insight on how to draw resonance forms. But now it's time for you to go out and start working on it on your own. And for that, I have a few last minute tips and reminders. Be sure to use your good arrow etiquette and draw neatly. Your professors will thank you for it. Look for multiple paths of conjugation, like we did in the examples earlier, whether that is taking resonance forms and seeing how they might resonate further, or if it's going back to your original molecule and looking for motifs that move in different directions. Never, ever, ever move a positive charge. Positive charges may end up in different locations across your resonance forms, but not because you're moving them. It's only because of the motion of the electrons, and that is one thing you are allowed to do. And last but not least, practice, practice, practice. Resonance can often be a tricky subject that students don't feel like they really grasp, but I promise you if you practice more with it and post any questions you have in the comments, you'll get a much better grasp on it. Thanks for watching.